Hi everybody, welcome to another video in Calculus 3, section 15.8, Lagrange Multipliers. What we do now, we'll still find the maximum and minimum, but not on a closed region like this. What we focus on is on the constraint, meaning that it's only on the boundaries. Remember, what we did on the previous section is something how we have the function try to find the maximum and minimum and on a closed region. Now what we focus on is on the boundary, and the boundary is given by a constraint or just a level set of some different region. Right, now what we focus on is to find maximum or minimum of the objective function, and we subtract to the constraint. The constraint is something like this: a function equal to 0. So if we have x squared plus y squared equal to 4, we can say x squared plus y squared minus 4 equal to 0, and that is our constraint in the problem. Right, x squared plus y squared minus 4, that will be g of xy in this case. So like I said, Lagrange multipliers we will find only on the boundary or from some certain condition like that. Right, the theorem. Let f be a differentiable function in the region contain a curve. Assume that it has a local max or min local extreme values at a point. Then the gradient is orthogonal to the line tangent to that. We already know that. Assume that the gradient of g is not equal to 0. It follows that the real number lambda satisfies this condition. So what we have is, it should be in this one. So we have a function. There will be a bunch of level set. Let me just plot. So we have the function that has a bunch of level curve. On those level curve, the values of the function equal to a constant. Like for example, this function equal to a constant corresponding to a curve. And then we have a constraint x squared plus y squared minus 4 equal to 0, something like that. So we will have, so we'll try to maximize or minimize, but the x and y must be in this constraint. So we have the level set of the function, and then we have the constraint. On the solution, the maximum or minimum have to be in the red or in this constraint. And it says that the gradient of the level curve of f and the gradient of the constraint must align, meaning that will point in the same direction. So because they point in the same direction, we have one is multiple of the other. So that is the Lagrange multipliers. This called lambda. Right. Now the method of Lagrange multipliers. So let the objective function, the function that to be maximized or minimized, be differentiable, and g also differentiable with the gradient not equal to 0 on the curve. To locate the maximum and minimum, what we do is the Lagrange multipliers is this equation. So the gradient of f points in the same direction as the gradient of g. I mean in the same direction, it could be in the same direction or opposite, but the gradient one is the multiple of the other. But if we do that, there will be two equations of two variables, not enough, so we have to take the constraint itself. And we solve this system of equation, and then we test them to see which one is the max, which one is the mean. So if you did not bring this out, because that is pretty much the whole section is about. So the gradient of the function align with the gradient of the constraint, and then the constraint itself, right? And the method of Lagrange multipliers. Is that right? Now, if you look at different books, usually engineering books, they're not going to write like this. What they do is instead they will write define the function L to be the function plus lambda times g of xy, and then they just take partial derivative with respect to x, with respect to y, with respect to lambda, and we have this. By the way, if we have this, you can write as f of x of xy is equal to negative lambda g of x of xy, f sub y of xy equal negative lambda g of y xy, right? And then the constraint itself. Now, to show that these two are extremely similar, I will write what do we mean when we say the gradient are equivalent. So from here, the gradient, of course, is partial derivative with respect to x. I'm not going to write x and y, so just have space. And then the gradient of g is g of x, g of y. Those two are equal. I mean, this equation give us f of x equal to lambda g of x and f of y equal lambda g of y. So we have this equation, these two equations, instead of these two equations. Those are the same, except one of them is lambda, one of them is negative lambda, right? We have f of x equal to g of x. Here we have negative lambda, here we have lambda. So whether it's positive or negative, it doesn't matter, because lambda should be a constant. So that's why in the engineering, most of the engineering book, they will refer to write like this. They will say to construct one function, they will take partial derivative with respect to x, y, and lambda. We're going to just have the same system of equation, because bottom line is we don't solve for lambda, we solve for x and y will be the same for those two system of equation. Alright, so by the way, when we go to an example, you will see small details. Alright, let's find the maximum and minimum values of the objective function. So we try to find the maximum and minimum of that function subject to this constraint, right? So I'm going to use the one that I've asked you to write, so we're going to use that. So first of all, this is g of xy, that is f of xy, that's nice. So first we're going to have the gradient of f of xy equal to lambda times the gradient of g of xy, and then we have g of xy equal to 0. So this is the method of Lagrange multiplier. Now, the gradient is partial derivative with respect to x, so we have f of x of xy equal lambda g of x of xy, and the gradient has the partial derivative to g of xy so we take the partial derivative and we match with the other with the constraint, and then finally the constraint itself. So those equivalent to this system. Right, let's just write out. Derivative of f with respect to x will be 4x equal to lambda. Derivative of g with respect to x is 2x. Next, derivative of f with respect to y, 2y equal lambda times derivative of g with respect to y, ay. And then finally the constraint itself, x squared plus 4y squared minus 4 equal to 0. Yeah, so we're going to solve this system of equations. That is not a linear system, it's not linear because of this power. So there's a lot of different ways to do it. We can solve for lambda, we can solve for x, elimination, substitution. There are quite a few ways to do it. Right. Right. So let's just rewrite this. 4x equal to 2 lambda x, 2y equal to 8 lambda y. We cannot divide by x on both sides or y on both sides here because x and y potentially be 0, so we cannot do that. Right. Or we can do elimination. If we multiply y here and multiply x here, we can eliminate. Alright, so what I do is I'll use elimination. So what we do, I will multiply the top equation by y here. Better yet, multiply by 4y. And the bottom multiply by negative x. Right. So that system become 4y times this give us 16xy equal to, and that give us 8 lambda x y. And negative x give us 2x, negative 2 xy equal to negative 8 lambda xy. Because then that constraint. Now if you add side by side here, those two cancel out, we just have 16 minus 2, so that's 14xy. So when we add side by side those two equations, add side by side, we have 14xy equal to 0, and then of course x squared plus 4y squared minus 4. So what we did here is, when we do this elimination, we eliminate lambda. So now we just have the system of x and y. So this will be easy to solve. The top one though, 14 times x times y equal to 0. That means either x is equal to 0 or y is equal to 0. Right? Because the product is 0, one of them must be 0. And then we can just substitute in here and we find y. So that should be easy. Right? Now, for x equal to 0, for x equal to 0, we will have I'm going to put 0 in here. 0 square plus 4y square minus 4 equal to 0. So suddenly I can solve for y. Y square minus 1 equal to 0. Y square equal to 1. So y equal to, don't forget there's plus or minus. So we have the point 0 and 1 and 0 and -1. 2 points. That's when x equal to 0. When y equal to 0, again I'm going to substitute in this equation. So that's 0. X squared minus 4 equal to 0. So x squared equal to 4. So x equal to plus or minus square root of 4, which is plus or minus 2. So we will have the point x equal to 2, y equal to 0, x equal to -2, y equal to 0. So those are the points. 4 points. 1, 2, 3, and 4. And we find the points. So after that, we just evaluate into the function to determine which one is the max, which one is the mean. So next one is just a table. Right, x equal to 0 and 1, 0 and -1, 2 and 0, -2 and 0. The function we try to maximize or minimize is 2x squared plus y squared plus 2. We can use calculator here, but this one is simple enough. I'm just going to do it by hand. Right, x equal to 0, y equal to 1. If y equal to 1, put 1 or -1 in here. X is 0, so that will be 3. And when y equal to 0 and x equal to 2 or -2, that is 2 squared is 4 times 2 is 8 plus 2 is 10. So we'll say maximum equal to 10 at the point 2, 0 or -2, 0. And then minimum equal to 3 at the point 0 and -1 or 0 and 1. Right. So once again, with the Lagrange multipliers, the method of Lagrange multipliers, we're going to let the gradient of f be multiple of the gradient of g. So we do that. Partial derivative with respect to x, partial derivative with respect to y must be multiple of each other, and then the constraint itself. Now if I'm going to write this in objective function, it will be very similar. Right. So I'm going to write the function. I will construct what we call the L equal to f of xy plus lambda of g of xy. Now I put everything into just one function. F of x is 2x squared plus y squared plus 2 plus lambda g of xy x squared plus 4y squared minus 4. So I construct one function like this. I'll get back to this in a minute. Right. So we construct this function, and I will multiply it out to x squared plus y squared plus 2 plus lambda x squared plus 4 times lambda y squared minus 4 lambda. What I do is I will find the critical point for L. So I take the derivative of L with respect to x. Derivative of L with respect to x, that will be 4x squared, 4x plus 2 lambda x. Derivative of L with respect to y, 2y plus 8 lambda y. And then derivative with respect to lambda equal to x squared plus 4y squared minus 4 equal to 0. Now, the reason we make all of this equal to 0 because to find a critical point, we find partial derivative to make that equal to 0, right? So that's why we have it this. And by the way, if you look at this, I will move the 2 lambda x to the other side. Same thing here. And then this will be the same. Now if we look at this system of equation compared to this system of equation, this is almost the same, right? Except, this system of equation, it is exactly the same. I'm talking about this and this. The only difference is here we have the minus, here we don't. But like I said, lambda is a constant, so it doesn't matter. So either we're going to let the partial derivative equal to multiple of partial derivative of the constraint, or we will construct an objective function like this, an objective function, and then take the partial derivative equal to 0. So we find the objective function and then the constraint times multipliers, and then we find a critical point for that partial derivative equal to 0. Bottom line is we should have the system of equation that produce the same solution. So whether we construct one big function or we're just going to use this is the same thing essentially. Right. Once we find all the points, I won't be able to tell if it is a maximum or a minimum. So of course there's a test for the maximum minimum, but it will be a lot easier. Just go back to the function, evaluate it. It was maximum and a minimum. So simple enough, right? So it is the same problem, but on this graph, what we're trying to maximize is the function 2x squared plus y squared plus 2. So the graph of that is a paraboloid. Look like this. So what we do is, the constraint is, so we try to find the maximum on the paraboloid, and the constraint is, so the solution must be lie on this ellipse, and this ellipse is given by the constraint. And of course we see after we graph it, the minimum is 3, the maximum is 10. Right. Now, so certainly we have the constraint C here from given by that equation. So what we do is to find the maximum minimum, we have the function, right? 2x squared plus y squared equal to 2. And what we do is we draw the level set, a bunch of them. Here, if we let this function equal to a constant, we have a level set like this, or level set like this, level curve. And then we will find where it is there's the intersection of a level curve of the function with the constraint, and there is two intersection here. That is 0 and 1 and 0 and negative 1. And then there will be a different level set, level curve. When we let this equal to constant, we have a big level curve, and the intersection of the level curve of the function and the constraint are those 0 and 2, 0 and negative 2. So essentially, in terms of graph, what we're trying to find is we have the constraint, and so we just graph a bunch of level sets, and if the level set, and then we find the intersection on the level set. That gives us the maximum and minimum. Of course, if we have like this, let's say there's a 4 intersection, so we have those two as well. However, at those points, the gradient do not align. Notice that, let's say at this point, right, we have a level set here and the curve. At that point, the gradient is pointing that direction. Or like, the reason I know it's pointing in that direction because that is orthogonal to the tangent vector. And then if the curve goes like this, the gradient point in that direction. So those two do not align. However, the point here, the gradient would be point in that direction for that curve. And for this level set, it point in the same direction. So essentially we want the gradient point in the same direction. The gradient of the level set or the level curve must be pointing in the same direction, as the gradient of the curve. And that's the idea of Lagrange multipliers. There's a bunch of intersection, but those two do not align. We only find the point where the gradient point in that direction, so it is orthogonal to the tangent, and then also point in the same direction. So at those points can be found using the Lagrange multipliers, and that's essentially what this theorem is about. So essentially, what we're trying to find is maximum or minimum of a function for a given boundary or the constraint. Right. We have another example, but before we do that, I just want to go back to the previous section. This is page 84, section 15.7, the last example. On the last example, we try to find the maximum and minimum of that function on the closed region. The focus here is we go find the maximum and minimum of that function on this line. I'm trying to find the focus on this line. So the problem will be as follows. I'm going to do the same, trying to find maximize or minimize. So maximize or minimize this function. You don't have to write this down. I just want to show you quickly. So we have the objective function, and then we would do find the maximum minimum on that boundary. So this is subject to the constraint. X plus y equal to 15. Yeah, so which is this line. So we're going to do this, see what happens. Right. First of all, x plus y equal to 15. We can turn this into x plus y minus 15 equal to 0. And that is g of xy. So g of xy equal to x plus y minus 15. Right. So we have the constraint and we have the objective function. Right. Lagrange multipliers. The gradient must align. The gradient of f must be the multiple of a gradient of g. So that's why we call Lagrange multipliers. So that means it's just multiply is the multiple of the other one. And then we still need the constraint itself. I'm just going to write in general, sorry. And then g of xy equal to 0. Yeah. Right. So I will take the partial derivative of f with respect to x. Those will be multiple of partial derivative of g with respect to x. Partial derivative of y must be multiple of partial derivative of g with respect to y. And finally, the constraint itself, x plus y once again, I just want to write the general case. G of xy equal to 0. Right, so that system of equation. Equivalently, derivative of f with respect to x, derivative of this with respect to x will be y minus h, and that's all there's to it. Lambda, derivative of g with respect to x, this is just 1. Now derivative of y f with respect to y will be negative 2y. Sorry, I forgot this. It will be derivative of this with respect to y will be x. Derivative of this with respect to y will be x minus 2y. The problem has no y square, so sorry, copy the wrong problem incorrectly. So that would be 12. So derivative of this function with respect to y is that equal to lambda times derivative of g with respect to y, which is 1. And finally, the constraint itself. Right, we write this equation, we will have y minus 8 equal to lambda x minus 2y plus 12 equal to lambda. Since both of them equal to lambda, they should equal each other. Right, so both of them equal to lambda, so we make them equal each other. Right, the reason we need 3 equations because we have x and y, so those are 2 equations. We need the constraint because there are 3 variables here with lambda as well. We don't need to solve for lambda, we just need x and y. So usually if there's a chance, I will eliminate lambda. So things will get easier after that. Right, so both of them equal to lambda. So we put them together and we will have y minus 8 equal to x minus 12, x minus 2y plus 12. And then the second equation. So we will have the system of only 2 variables because we eliminate lambda. And then x plus y minus 15 equal to 0. Right, move everything on one side. What I mean is keep x and y on one side. and move the y to the other side here, become x minus 3y, right? Minus 3y, move the 12 to the other side, and then move the 15 to the other side. We have x plus y equal to 15. So this is the system of equation. Right. I think I showed you how to use the matrix to solve the system of equation. Second matrix, turn it on. Second matrix, go to math and go to reduce row echelon form and hit alpha zoom. This is the 2 row 3 columns matrix. Will be 1, -3, -20, 1, 1, and 15. Of course, we have 6.25 and 8.75. Right, that's one way to do it. Or we can just go to reduce row echelon form, and then we enter the matrix. If we want to enter the matrix, hit second matrix, go to edit, and let's say 2 row 3 column. Now we enter the matrix. 1 for x, -3 for y, -20, and in here we can hit enter. On the home screen we cannot hit enter. It's 1, enter, 1, enter, 15. Right, and then we do reduce row echelon form, and then second matrix, highlight in the names, we call out the matrix A. If we want to input the matrix, go here to input the matrix. If we want to recall a matrix, keep it here, names, and then highlight 1, so we still have the same thing. Or we just do this by hand. Yeah, just elimination or substitution. Just try to eliminate x, for example. Multiply the top equation by -1. So I will have -x plus 3y equal to 20, and then x plus y equal to 15. Add side by side, x cancel out, 4y is equal to 35. So y equal to 35 divided by 4. Should be 8.75. And we can substitute this back in this y. So x plus 8.75 equal to 15. So x equal to 15 minus that will be 6.25. So we have x and we have y. And on the previous section, we did indeed have x equal to 6.25 and y equal to 8.75. We do it differently. We say because it is on this line, we can just substitute y equal to 15 minus x, and we have the function of x, take the derivative of it, equal to 0. So yeah, certainly we can use this parameterized method. Here I use Lagrange multipliers. So bottom line is we have the objective function, try to find maximum minimum point subject to the constraint or the equation, and then we can use Lagrange multipliers. We should have the same thing as when we parameterize it. Right. I thought I could show you that so that we can confirm our answer previously. Right, now we have one more example. Find the maximum minimum of this function subject to that constraint. So I should move everything on one side and make it g of xy, x squared plus 2y squared subtract 4. Yeah, g of xy should be equal to 0. Right. Now we will write the system. Of course, I'm not going to just write that again. It doesn't hurt. So the gradient of f must be multiple of the gradient of g. And then we have the constraint itself. Right. And the gradient will have the partial derivative with respect to x and partial derivative with respect to y. Those must be also multiple of partial derivative of g with respect to x, partial derivative of g with respect to y, and then the constraint itself. So this is the system of equation where we solve for x and y. We don't need to solve for lambda. Right. Derivative of f with respect to x, negative ax. Derivative of, and then equal to lambda, derivative of g with respect to x, 2x. Derivative of y, and derivative of f with respect to y, 2y, equal to lambda times derivative of g with respect to y, for y. And then the constraint itself. Equal to 0. Right. Now, just like what we did earlier, we use elimination or substitution. The point here is if we're not looking for lambda, it would be a good idea if we eliminate it. So to eliminate lambda, I will multiply it. We need to have xy here. So multiply by y. And then a 2 to make it 4. And multiply by negative when we add it. So that gives us negative 4 lambda xy. And here we multiply by x. Those we eliminate the lambda here. So we have 16 xy equal to negative 4 lambda xy, 2xy equal to 4 lambda xy. And then we still have x squared plus 2y squared minus 4 equal to 0. Yeah. So if we add side by side, the left hand side is 18xy, the right hand side is equal to 0. Since we eliminate lambda, we have 2 variables left. We only need 2 equations. And once again, 18xy equal to 0. So that gives us either x equal to 0 or y equal to 0. Simple enough, right? Now x equal to 0, put in here and find x. Y equal to 0, put in here and find y. X equal to 0, put in there and find y, and then y equal to 0 and find x. Right. There's more space on the next page if you bring out the note. So for x equal to 0, we will do this equation, 0 squared plus 2y squared minus 4 equal to 0. So we solve for y squared here. 4 divided by 2. So y squared is equal to 2. So y equal to plus or minus square root of 2. So we have the point 0 square root of 2 and 0 negative square root of 2. Similarly, for y equal to 0, put 0 in for y. We have x squared y equal to 0. So give us x squared equal to 4. So x equal to plus or minus square root of 4, which is plus or minus 2. So we have the point x equal to 2, y equal to 0, and x negative 2 equal to 0. And then we put in the table, find the maximum and minimum. The function we will try to maximize or minimize is y squared minus 4x squared. X equal to 0 square root of 2, 0 negative square root of 2, or 2, 0 negative 2, 0. Right. Now this should be easy. When x equal to 0, y equal to square root of 2, put it there, we should have 2 and 2. X equal to 0 and y equal to that. Now, when y equal to 0, and we put x in here, 2 and negative 2 in there, 2 squared is 4 times negative 4 is negative 16. So maximum and minimum there. So maximum equal to 2 at the point 0 square root of 2 or 0 negative square root of 2. Minimum equal to negative 16 at x equal to 2, y equal to 0, or x equal to negative 2, y equal to 0. Right, so that's simple enough. So as we see that usually the way we solve for the system is we try to eliminate lambda. Or we could solve for lambda, and there's a lot of different ways to solve the system of equation. Here I'm just going to eliminate lambda because bottom line is we're looking for x and y. Right. So other types of Lagrange multipliers. So essentially we may have the function of 3 variables. And we might, in that case, we still do the same thing. The gradient, in this case, partial derivative with respect to x, with respect to y, and with respect to z. So there are 3 equations. Plus the constraint will be 4. So there will be 4 equations in that system. Or we can construct one big function and then find partial derivative with respect to x, y, z, and lambda. Also 4 functions. Or we might have 2 constraints. If we have 2 constraints, then we have lambda, and then we have mu, and then we do that, and then we have 2 functions, 2 constraints, and then 2 constraints itself. So this equation should have 5 variables, x, y, z, lambda, and mu. Or we can construct that. Usually you should not have this kind of question on the test because that's too complicated. Equation of 5 variables. That's not a practical thing to do on the test. So I'm not going to ask you that. So bottom line is just have the system partial derivative equal to multiple of the partial derivative of the constraint and then the constraint itself. So that system of equation, get the point where we get the points, put back into the function, and then we can find the maximum and minimum from there. There is the test to show that it is the maximum or the minimum, which we don't need to. We just show that it is the maximum, is the minimum from the table. Because after all, when we find the maximum minimum here, it's going to be an absolute maximum and absolute minimum. Right. That's what we have. I just want to, because we still have, I think, should have a little more time on this, so we, again, just go back and to solve the system equation here. On this one, we cannot divide by x on both sides, because x potentially can be 0, and indeed x is 0 is one of the solutions, so we do not divide by x on both sides. Right. If we want to, we can solve like this. And from this one, we can pull out on both sides and factor. We can factor out 2x. So either we have x equal to 0 or lambda equal to 2. So of course we have x equal to 0. Now if we have lambda equal to 2, we put into the second equation 2y equal to 8 times 2 times y. So we have 2y equal to 16y. Of course the only thing could happen is when y equal to 0. So potentially we might have x equal to 0, and then we can solve for y after that. Or we can have lambda equal to 2. If lambda equal to 2, y is equal to 0. Now we know y is equal to 0. Put it back in the equation to find x. So yeah, so certainly we can solve for x. Don't divide by both sides, just move everything on one side and factor. So we can solve for x and y. Or we can potentially solve for lambda and make them equal. So that is the example that I showed earlier. Since both of them equal to lambda, we make them equal. So potentially if we can solve for lambda, we can make them equal. On this problem, I cannot solve for lambda. I do, but don't divide by x on both sides. So bottom line is the system of equation, system of nonlinear equation, there are a lot of different ways to do it, and just depends on the problem. Sometimes try to solve for lambda or try to eliminate lambda is a good way to go, because we're not looking for lambda, we just need x and y. Right. And finally, just want to emphasize that the problem is pretty much this: partial derivative of f and g must be multiple of each other. Partial derivative with respect to x and with respect to y must be multiple of the other, and then the constraint itself. Those together is the system of equation for Lagrange multiplier. The problem that use Lagrange multiplier, and Lagrange multiplier is we use that to find the maximum and minimum of an objective function on the boundary. So this should be equal to, or on the boundary, yeah, equal to. Right, and with that, I stopped section 15.8 here. As always, thank you for watching.